From the delicate motion of particles to the massive movement of galaxies, the universe runs on a framework of rules we call the laws of physics. Most people think of those laws as permanent, irrefutable truths that keep reality in place. But what if some of the very laws holding the whole universe together are also the most bizarre, the most counterintuitive, and often overlooked? Well, stay with us, because today we're about to explore some of the strangest laws of physics. Time dilation. Albert Einstein was the man who shattered one of the oldest assumptions people ever had about reality, that time moves the same way for everyone. It feels obvious, doesn't it? A second is a second. An hour is an hour. Time just keeps moving forward. But according to Einstein, that is not actually true. According to special relativity, and the faster something moves, the slower time passes for it compared to something moving more slowly. That means if two identical clocks exist, and one stays on Earth while the other is sent through space at an enormous speed, the moving clock will come back, showing less time has passed. Not because it failed, but because time itself slowed down. And then it gets even stranger. General relativity says gravity also affects time. The stronger the gravitational field, the slower time moves. So time actually passes a little faster at the top of a mountain than it does at sea level. The difference is tiny, but it's real. Now, this is not just some wild theory scientists like talking about. GPS satellites have to account for time dilation constantly. If they didn't, well, let's say your location would start drifting badly. In fact, then even the famous twin paradox comes from this same idea. One twin travels through space at extreme speed, returns home, and ends up younger than the one who stayed behind. And that is what makes time dilation so disturbing. Time is not this solid, universal thing we all share equally. It bends depending on speed, gravity, and where you are in the universe. Black hole information paradox. Black holes are some of the most fascinating and mind-boggling objects in the universe. Now, we know that they are super dense. Their gravitational force is so insanely strong that nothing, not even light, can escape once it crosses the boundary, which scientists call the event horizon. But the real issue starts after that, because once something falls in, physics runs into a problem it still hasn't fully solved. This is what scientists call the black hole information paradox, and it has been causing trouble for decades. The problem became famous in 1976, when Stephen Hawking argued that black holes are not completely black after all. According to his work, they slowly lose energy through what is now called Hawking radiation, and over unimaginable stretches of time, they can eventually evaporate. And that is where everything falls apart. If a black hole can disappear, then what happens to all the information carried by everything that ever fell into it? According to quantum mechanics, information cannot simply be erased from the universe. But according to the old picture of black holes, anything crossing the event horizon is gone for eternity. That creates a direct collision between Einstein's general relativity and quantum theory, two of the most successful ideas in science, and they do not agree. Over the years, physicists have proposed all kinds of answers. Some think the information is somehow stored on the black hole's surface. Others have given strange ideas like firewalls, fuzzballs, or hidden quantum links between the inside and outside of the black hole. In 2012, physicist Stephen Giddings proposed one of the more intriguing possibilities, that information may escape through a subtle kind of non-local quantum link. And now, this is where it gets even wilder. A recent Caltech preprint suggested that future detectors like LISA, approved by the European Space Agency in 2024, might actually look for tiny distortions in gravitational waves that could hint at whether that idea is real. So black holes do not just swallow stars. They also expose a crack in the laws of reality itself. The quantum chess cat. Well, now, before you start imagining a cat playing chess, this has absolutely nothing to do with that. The name actually comes from Lewis Carroll's Cheshire Cat, the strange creature in Alice in Wonderland that could disappear and leave only its grin behind. And as ridiculous as that sounds, quantum physics somehow found a way to make it feel almost real. This idea is called the quantum Cheshire Cat, and it describes a bizarre situation where a particle can appear to be separated from one of its own properties. In simple terms, the particle is in one place, while something that belongs to it, like its spin or polarization, seems to show up somewhere else. That should not make sense. In everyday life, an object and its properties come together. A ball cannot roll one way while its color wanders off into another room. But in the quantum world, things stop behaving like common sense ever had any authority there to begin with. This strange effect was not just dreamed up for philosophy class. Back in 2013, researchers reported experimental evidence of it using neutrons, and later, similar ideas were explored with photons. The setup said that the particle itself traveled through one path, while one of its measurable properties behaved as if it had taken another. And that is what makes this so unnerving. It forces you to ask a very uncomfortable question. If a particle can be separated from what makes it what it is, then what exactly are we even looking at when we say something is there? The quantum Cheshire Cat is one of those ideas that reminds you that quantum mechanics is not only strange, it is operating on a level of reality that seems to ignore the rules our brains were built to trust. The Unruh effect. The Unruh effect, also known as the Fulling-Davies Unruh effect, is one of those ideas that sounds completely absurd until you realize physicists take it very seriously. It begins with a question that seems simple. Is empty space really empty? According to quantum field theory, not even close. What we call a vacuum is not truly nothing. Even in empty space, tiny quantum fluctuations are constantly flickering in and out of existence. Most of the time, we never notice them. But according to physicist William Unruh, who proposed this in 1976, it can change depending on how you move. Here is the bizarre part. If you were floating motionless through empty space, you would detect nothing unusual. But if you started accelerating hard enough, that same vacuum would begin to look warm, like literally. To an accelerating observer, empty space would appear filled with a faint bath of particles, almost like heat rising out of nowhere. That means temperature itself may not be as objective as it seems. The faster you accelerate, the hotter the vacuum appears. And that is deeply strange, because it suggests reality does not always look the same to everyone. Even nothing depends on who is observing it and how they are moving. The problem is, the effect is incredibly difficult to test. The acceleration needed to detect Unruh radiation directly is so extreme, it is roughly 1 quadrillion times stronger than Earth's gravity. But researchers at MIT and the University of Waterloo have been working on ways around that, including methods involving accelerated atoms and electromagnetic fields. And here is what makes this even more important. The Unruh effect is mathematically tied to Hawking radiation, which means understanding this strange heat from motion effect could help scientists understand what black holes are really doing. In physics, even empty space can burn. The law of least action. This law might sound like one of those physics ideas designed to scare people off before it even begins, but once you understand it, it becomes one of the strangest and most beautiful things in science. At the center of it is a simple but almost eerie idea. Nature does not move randomly. It seems to follow the path that works best. And this idea was turned into something far more powerful by William Rowan Hamilton, and over time, it became one of the deepest foundations in physics. It helps explain why things move the way they do, from a falling object to the motion of planets, and even the strange behavior of particles. Here's what makes it so fascinating. If something moves from one place to another, there are countless ways that motion could happen. A particle, for example, could take all kinds of imaginable paths between 2 points. But in reality, only one of those paths is the one nature actually uses. According to Hamilton's principle, that path is the one where something called action, written as S, becomes stationary. That action is built from the Lagrangian, which is simply kinetic energy minus potential energy. And somehow, from that balance alone, motion begins to make sense. And that is what makes this law feel so strange. It almost feels as though nature is not merely moving, but calculating. And somehow, from falling objects to orbiting planets, the same principle keeps showing up again and again. The Casimir effect. Physics is a strange subject because the closer you look at reality, the less predictable it starts to feel. One of the best examples of that is the Casimir effect, a phenomenon that completely ruins the idea that empty space is truly empty. In 1948, Dutch physicist Hendrik Casimir proposed something that sounded impossible at the time. He suggested that if you place 2 perfectly smooth metal plates extremely close to each other inside a vacuum, they will begin to drift together on their own. Nothing touches them. Nothing visible pushes them. And yet, they move. And the reason comes from quantum field theory, which says that even a vacuum is not truly silent or inactive. What looks empty is filled with tiny quantum fluctuations constantly appearing and disappearing in the background. When the 2 plates are placed close enough together, they limit those fluctuations in the narrow space between them. Outside the plates, there is slightly more activity. That tiny imbalance creates pressure, and that pressure pushes the plates inward. It is such a small effect that it only becomes noticeable at tiny distances, but it is real, and scientists have measured it. It has totally changed the way we think about nothingness. The arrow of time. Now, we have a very easy question for you. Why can't we go back in time? Why does everything in life seem to move in only one direction? You can remember yesterday, but you cannot return to it. You can imagine tomorrow, but you can't skip ahead and meet it early. We mean, no matter who you are, time keeps dragging everything forward. And that is what makes the arrow of time so weird. Because when physicists looked closely, they found something deeply strange. Most of the fundamental laws of physics do not actually care which direction time is moving. On paper, many of them work just as well forward as they do backward. A planet can orbit, a particle can collide. The equations do not panic if you reverse the film, but real life clearly does. A glass falls and shatters. It never leaps off the floor and rebuilds itself, as we've seen in many movies. We grow older, not younger. Smoke spreads through a room, but it never returns to the cigarette. Something is forcing reality to move in one direction, and that something seems to be entropy. Entropy is often described as a measure of disorder, but really, it is about how systems naturally drift from order into a mess. Clean rooms become dirty, hot coffee turns cold, and the structure breaks down. And, according to the second law of thermodynamics, entropy in the universe tends to increase over time. That may sound abstract, but it could be the very reason time feels like it has a direction at all. And honestly, That is what makes this idea so haunting. The future may not be pulling us forward. It may simply be that the universe is constantly unraveling, and we are living inside that unraveling, 1 second at a time. It's strange, isn't it? Well, that's it. Thanks for watching, and be sure to like and subscribe. We'll see you next time.